So here's the first example. We are revisiting logarithmic differentiation. And the first one, you have a function that looks like this: y equal x raised to the power of sine x. So a mix of exponential function and trigonometric function. And we want to find y prime. So the solution. Remember, when we do logarithmic differentiation, it's a two-step dance. First, we're going to apply the natural log. We turn everything into a logarithm. And then we're going to apply implicit differentiation. So the first step, apply natural log. And we end up having the natural log of y equals sine x natural log of x. And now we differentiate or apply implicit differentiation and get the derivative of the natural log of y is y prime over y. We've seen that yesterday. The derivative of natural log is 1 over the argument, and hence we have 1 over y, and then the derivative of y is y prime. And on the right side we have the product rule, so we end up having cosine x times natural log of x plus sine x times 1 over x. And to bring it home, we need to multiply by y. So y prime equals y times cosine x times natural log of x plus sine of x over x. Okay, and substitute y with x raised to the power of sine x, and this pretty much complete the exercise. Earlier this morning, a student asked me if we can replace the expression, the term sine x over x with 1, as the limit is still fresh in our mind, the limit. But remember, this is the limit as x approaches 0. So, yeah, if x approaches 0, then we can do that. But on the other hand, the natural log of 0 is undefined. So the whole solution, y prime, is undefined for x equals 0. Okay. The other thing is x equals 0. Look at the function that we started with. It's 0 raised to the power of sine of 0. So it's 0 raised to the power of 0. Well, that's another one of these deals where the function is undefined. 0 raised to the power of 0 is undefined. Later in the semester, we're going to look at a family of functions that have this 0 raised to the power of 0, 0 times 0, infinity times infinity, and so on. And we devote a section to the treatment of these functions. Next example. Very similar to the first one, we have y, but we'll do role reversal. Here we have x raised to some trigonometric function, and now we'll do the opposite, sort of. We're going to have a trigonometric function. In this case, it would be cosine of x raised to the power of x. Okay. And as before, we need to find y prime. And as before, we're going to start with applying the natural log. As after all, this section is about logarithmic differentiation. And we end up having the natural log of y equals x times the natural log of cosine x. Like so. And when we implicitly differentiate both sides, we get y prime over y, and here we have 1 times the natural log of cosine x plus x times, and here I have a little bit of chain rule. The derivative of the natural log is 1 over the argument, so we'll have 1 over cosine x, but the derivative of the cosine is the negative sign. And we correctly recognize that we have a tangent here. So indeed we simplify it a bit, and we end up y prime over y equal natural log of a cosine x minus x tangent x. And now all we need to do to complete is multiply the whole thing by y, which is cosine x raised to the power of x, and we are done. And the last one in this group, we have a function looks like this, y equals the natural log of x times e to the power of x squared. So notice that the argument of the function of the natural log is x e to the power of x squared. In this case, we want to find the equation of a tangent. And we'll do it at x equals 1. So you want to take a minute, look at this, or a few seconds, look at the problem, and develop a strategy here. Think about what do we need in order to solve this. Well, in order to come up with the equation of a tangent, we need a point and we need a slope. Well, the slope will be the derivative at x equals 1, but in order to get the point, we need to evaluate y at this point. So, y, when x equals 1, we're simply going to substitute x with 1 will be natural log of 1 times e to the power of 1 squared, like so. And turn out that this will be the natural log of e, and the natural log of e is 1. So the point where the tangent, where we're going to look for the tangent will be xy equals 1, 1. And the slope of the tangent is y prime at x equals 1, right? Actually, I'm a little bit premature here because let's first find y prime in general. So in general, y prime will be the derivative of the function we started with. Here we don't have to do logarithmic differentiation because we have already a logarithm. Again, the argument is x times e to the x squared. The derivative of the natural log is 1 over the argument. So it would be 1 over x times e to the x squared. And then we multiply by the derivative of x e to the x squared. Well, we have a product here, so we need to apply the product rule. The derivative of x is 1, and then e to the x squared plus x times the derivative of e to the x squared. So let's see. E to the u, the derivative is e to the u, so it's going to be e to the x squared, and then we need to multiply by the derivative of x squared, which is 2x. Okay. Now, this is y prime. I can simplify it a little bit. Indeed, I'll simplify it, but For those of you who don't want to simplify, if you want to stay like goal-oriented, what you want to do is find the slope of the tangent, or the derivative at x equals 1. So you can go ahead and replace x with 1 at this point, but it's kind of not neat. So for the sake of neatness, we're going to see that we have e to the x squared as a common factor, and if you factor it, you have 1 plus 2x squared. All of it divided by x times e to the x squared. Well, further simplification will give you 1 plus 2x squared over x. That's a very nice compact form of the derivative. So this is where we are. Y prime equals 1 plus 2x squared over x, and therefore the slope of the tangent is y prime at x equals 1, or 1 plus 2 times 1 squared over 1, and of course it's equal to 3. So at this point we have the point at this time we have the point xy equal 1, 1, and the slope of the tangent equals 3. So the tangent is y equals 3 times x minus 1 plus 1, and this will give you 3x minus 2. And normally what I like to do at this point is graph the function, graph the tangent, and see if indeed the tangent touches the curve of the function at 1, 1. But this is something you can do on your own.